Okay, this next chapter is called irrational equations or irrational functions. It's the same idea as before. We're just changing the parent function or the parent graph of what we've been looking at. To mean something is irrational, we're typically dealing with the function of y equals the square root of x. It's this square root or this radical sign that makes this irrational. Something we want to remember about square roots or cube roots or any of those type of things is that we can rewrite the square root of x to equal x to the 1/2. This follows a lot of rules that go, say, the cube root then of x is equal to x to the 1/3. This follows a specific pattern. So if you have, say, the x to the 1/7, that's your cue that this is x to the 7th root. And then if this number isn't a 1 on the fraction, if we have something like x to the 2/5, what's that saying is that this is equal to the 5th root of x squared. So overall, the golden rule here is that if x is raised to 1 over any n, it's the same as saying x to the nth root. Okay, so that's what these irrational equations are. Again, it's just getting you kind of used to the idea of square roots. Let's take a look at some examples of square roots. Okay, let's go over how to find the square root of odd numbers like this. Well, not odd numbers, this is an even number, but still just numbers that they don't have a perfect square. 288 is not a perfect square. And even if you didn't know it was a perfect square, we can still use this technique to find what the square roots are. So the best thing to do is just take 288 and divide by a perfect square. The first perfect square that I'm going to try to divide by is 4. There's an 8 here. It's an even number. Something tells me that 4 is probably a good starting point. So I'm going to divide by 4. I'll do it on this side. So divide by 4. That's going to give me 72. Okay. Looking at 72, again, I want to ask what is this? What can divide into this as a perfect square? If I think to myself, it looks like 4 might do it again. So I'm going to try 4 again, and which is going to give me 18. And then from here, the next perfect square I want to divide by, well, I know 9 goes into this. Okay, so really 288, okay, or this square root of 288 can be rewritten as the square root of 4 times 4 times 9. If you divide 18 by 9, you get 2, and so times 2. There we are. Okay. And let me erase this so it's kind of out of the way. Okay, so we know what the square root of 4 is, we know what the square root of 4 is, and we know what the square root of 9 is. 2 does not have a perfect square. The square root of root 2 is the square root of root 2. So root 2 equals root 2. So what's the square root of 4? It's 2. What's the square root of 4? It's 2. What's the square root of 9? It's 3. And then the square root of 2 is the square root of 2. Now I'll multiply all these together. And this is 4 times 3 is 12. Root 2 is the square root of 288. Okay? So, again, what we've done here is I've broken this down into perfect squares that go into 288. That can sometimes take some checking and guessing. And then once I found my perfect squares, I take the square root, and then I multiply all those together on the outside of the irrational symbol, which is going to give me that 12 root 2 is equal to the square root of 288. Okay, again, the trick here is that we are dividing by perfect squares. Okay, dividing by perfect squares. Okay, next I want to talk about what the square root of x graph looks like. So y equals the square root of x. So if we were to build a table, okay, what's the square root of 0? Is 0. The square root of 1 is 1. If I put in 2, the square root of 2 is, well, square root of 2. And I don't want to go looking for a decimal approximation of this. So I'm just actually, for the rest of them, I'm going to choose perfect squares. So let's see, when x is 4, I know y will equal 2. When x is 9, y will equal 3. Okay, so I'm using this as my table. If I were to go in and graph this, 1 is to 1, 4 is to 2, and 9 is to 3. And this is a graph that's looking like, I don't know, I call these lazy graphs because they kind of go up kind of quick, but then they get really lazy and kind of flat as they go through. Another way to think of it is, well, this is just a half of a parabola, okay? It's a parabola on its side. Okay, last thing I want to talk about is sometimes we, or maybe you've been taught that that the answer to the square root of x is actually, or sorry, if we had y equals x squared, this would come out to be, well, plus or minus, y equals plus or minus x. Maybe you've learned that in the past somewhere. However, we need to completely ignore the negative answer. The reason we're ignoring the negative answer is because we're calling these irrational functions. Okay? The negative answer is going to give us this other side of the parabola, right? Okay? And however, once that happens, once we start to notice the negative part of this, this graph fails the line test. So therefore, it cannot be a function. So to call it a function, mathematicians ignore the negative part of the square root symbol. Okay, when we are graphing, we're not going to just see the square root of x every time. What we're going to see is we're going to see constants outside of the rationals, and we're going to see constants inside of the irrational or the radical symbol. What k is doing? K is going to be shifting graphs left and right. Okay, so when it's inside, this is going to shift left and right. Okay, and this c outside, the constant outside, this shifts our graph up or down. Okay, so that'll make the graph go like this. And again, we're going to be having a lazy graph. It's going to be something that goes like that. Okay, lazy graphs. In fact, maybe could you figure out what this graph is? Maybe you guys can try that at home. Okay, cool.